The moon isn't trying to kill you with vacuum. Not really. The thing that nearly ended Apollo missions early was dust. Not dirty shoes dust, microscopic, razor-edged grains that chew through seals, haze optics, clog joints, and mess with thermal systems. And if we're serious about building a lunar economy, bases, power plants, mining, comms, this dust becomes a brutal infrastructure problem. Right now, governments and private companies are spending real money to turn the moon into an industrial foothold. Not for flags, for logistics, communications, energy, science, and resilience. The contracts sound futuristic, but the risk is painfully normal: downtime. Because the moment you land vehicles repeatedly, drive rovers daily, and run habitats 24/7, dust stops being a nuisance and becomes a balance sheet item. Maintenance hours, replacement parts, schedule slips, mission risk, and insurance math. To understand why lunar dust is uniquely nasty, forget dust on Earth. On Earth, wind and water round particles down. On the moon, there's no rain, no rivers, no atmosphere to soften anything. Micrometeorite impacts pulverize rock, and the fragments stay sharp, jagged, abrasive. They don't get worn friendly over time. Now add charge. Sunlight and the space environment can electrically charge dust grains. So dust doesn't just fall, it clings, it migrates, it coats surfaces, it works its way into seams. Imagine glitter that behaves like broken glass and refuses to let go. Apollo learned this fast. Astronauts came back covered because it stuck to suits. Once inside the lunar module, it spread everywhere: air, instruments, seals. Crews reported irritation in eyes and throat after exposure, and hardware suffered. Abrasion, contamination, mechanisms getting gritty, seals degrading. Apollo was on the surface for days. A permanent presence means years, and years means compounding wear. So a modern lunar outpost needs separation as a core design principle. Keep dirty systems outside. Minimize dust entry. Use airlocks built for contamination control. Consider suit ports so suits stay outside instead of walking your dirt into the habitat. Then filtration becomes mission critical because you can't afford dust cycling through life support and sensitive electronics. Heat management is another pressure point. On the moon, thermal control is life control. Radiators need to dump heat, and dust on radiator surfaces can reduce performance. A thin coating can turn comfortable margin into "we have to throttle down systems" or "we have to shut something off." Then there's mobility. Anything that moves, wheels, bearings, hinges, drills, conveyors, has to survive dust ingestion. Servicing on Earth is cheap. Servicing on the moon is a launch manifest, a schedule window, and a resupply chain. So you either build mechanisms that tolerate dust, or you build active systems to keep dust away, or you accept constant downtime. And then comes the part people underestimate: landing operations. Lunar regolith can become a high-velocity sandblaster when rocket engines fire near the surface. Ejected particles can threaten nearby assets, habitats, power units, other vehicles, optics, solar arrays. If you want frequent landings, you eventually need prepared surfaces: pads, berms, stabilized zones. In other words, the moon becomes a construction site before it becomes a city. Now, what actually breaks? Seals fail silently. They don't explode. They degrade, leak a little, then a little more. Abrasion turns into cascading maintenance. Suit layers wear, visor coatings scratch, joints stiffen, connectors foul, sensors get blinded, solar panels lose output, thermal systems lose margin, and the human side matters too. If dust exposure forces shorter EVAs and stricter protocols, your productivity drops, and productivity is cost.
So the bottleneck isn't, can we land? We can land. The bottleneck is, can we keep hardware functioning long enough for operations to compound? Because compounding is how you get from missions to an economy. No compounding means no sustainable presence, just expensive, fragile sorties. This is why lunar dust is also a procurement story. The winners won't just be the companies with big rockets. The winners will own the unglamorous layers you can't skip. Spacesuits and EVA systems are one. If the suit is a dust magnet, the habitat becomes a dust trap. So next-gen suits are not just mobility, they're contamination control, abrasion resistance, reliable joints, better visors, better seals. In a real build-out, EVA capability becomes a recurring service, not a one-off hardware purchase. Dust mitigation is another. Coatings that resist abrasion, surfaces that reduce adhesion, cleaning methods for critical areas, filters that last. Anything that reduces maintenance cycles multiplies your effective budget and raises mission uptime. Surface preparation is another. Pads and stabilized zones sound boring, but they unlock cadence. Cadence is everything, because every delay costs money and slows learning. And slow learning is how space programs bleed budgets. Robotics is another. On the moon, labor is expensive and time is scarce. Robots can clean, inspect, move regolith, build berms, and do repetitive maintenance without consuming oxygen or EVA time. The economics will push toward automation fast because autonomy is cheaper than human minutes. So what happens in the next 24 months? Expect the story to shift from "we're going back" to "we're building." More emphasis on long-duration operations, not stunts. More hardware marketed around dust tolerance. More demonstrations of surface stabilization. And more contracting that pays for reliability, uptime, maintainability, repeatability, because that's what turns exploration into an industry. Here's the takeaway. Lunar dust isn't a side quest, it's the gatekeeper. Solve it at scale and you unlock compounding. More EVA, more construction, more power, more machines, more landings, more industry. Ignore it and every lunar plan stays trapped in the Apollo era, short visits and fragile hardware. So when you hear "city on the moon," ask one question: where does the dust go? Because the budgets are real, the timelines are aggressive, and the physics doesn't care. The dust is waiting, and it only cares about contact. And here's the good news. Lunar dust isn't some mysterious curse. It's an engineering problem. And engineering problems get solved the same way every time. Isolate the risk, design for it, and build systems that keep working when reality gets ugly. The moon is forcing us to level up. Better suits that don't bring the surface inside. Smarter airlocks and filtration that treat dust like a biohazard. Radiators and sensors designed to stay clean. Rovers and joints built to survive abrasion. And eventually, something that sounds boring but changes everything. Prepared landing pads and stabilized ground so every arrival doesn't sandblast your entire base. Once those pieces click, the moon stops being a place we visit and becomes a place we operate. Reliability turns into cadence. Cadence turns into cheaper logistics. Cheaper logistics turns into more missions, more construction, more science, and finally, real industry. That's what a lunar economy actually is. Not a single heroic landing, but thousands of normal days where machines run, systems stay stable, and the base just keeps going. So yes, the dust is the gatekeeper, but it's also the unlock. Because the moment we solve it, we're not just going back to the moon. We're building the first off-world supply chain in human history, and that's the step that makes everything after it possible.